nowadays.
फॉरवर्ड और बैकवर्ड
हाँ,
ये
ये
लीजिए,
अब इससे
इससे सर फॉरवर्ड जाएगा।
ये फॉरवर्ड के
ये
लिए है, ये क्या बैकवर्ड
सर ये
के लिए?
बैकवर्ड के लिए नहीं, बैकवर्ड के लिए आपको यही यूज़ करना पड़ेगा।
ये फिर ओके, yeah, actually. So, thank you. I'm happy to be here to give this talk. I was told that I was given from 2:30 till 3:15
सर ये आपका माइक नीचे है।
for the talk. I said I need more time. Um, it's no longer 2:30, I'm afraid. So, anyhow, I'm going to take the time that I need then. There was Turok and Hawking had a bet about Hawking's information loss paradox, and this was in 1997. Hardly anybody was bothered about it, except a few who were interested in black holes. Then Hawking had to pay for losing the bet in 2004, with claims of not being actually wrong, but admitting that he had lost the bet. That made it big news. Hawking was actually wrong. So, when I came across Hawking's work on radiation from black holes in 1976, I thought it was great, providing a halfway house on the way to quantization of gravity. That's the name it's given. However, I found that some of the ideas did not seem to lead to reasonable results. They were paradoxical. So, with that background, I'll be talking about the chronology of black hole thermodynamics. I've shown these two black hole paradoxes. I'll talk about the Carter-Penrose diagram, which is essential for discussion of general relativity, and I say there's ambiguity in there. And then go on to entropy in two-dimensional black holes and the suture model that Wheeler and I constructed. Is there Hawking radiation? That's the question. And then the information loss paradox and the conclusion. I have at the end a nearly classical resolution, time permitting, but already the time wasn't looking as if it was permitting, and now with Norese's help, it's not permitting. So that will be left alone. In 1968, Roger Penrose gave a seminar which I attended, I just joined in, and his idea was that you can use black holes to violate the second law of thermodynamics. He imagined a civilization built on a hollow Dyson sphere. A Dyson sphere is something that you'd expect an advanced civilization would construct around a sun so that all the energy could be used. Not just what reaches you, but the entire output could be used. So that is what people had postulated. And here he thought of the sphere, but being on the inside, you then can use that black hole. The civilization, as I say, is not only literally, but figuratively also built about the black hole, as that is the source of power for them. There's the black hole civilization, my cartoon figure for it. A box attached to a spring. I don't know if this will show this, yes. So here's the box attached to a spring over here, and you lower it down, but you first fill it with thermal radiation. All the radiation that would be around, You just open up the box, fill it up with thermal radiation automatically, close it, lower it down to the black hole, and open it. Then all the radiation will fall into the black hole, and you then raise it without the thermal radiation. So whatever had gone into the black hole is just in there. The amount of energy that you would have put in to raise the box would be the amount you had already obtained from lowering the box. But this extra bit of the thermal radiation would then be available as usable energy, and that would generate the energy for this civilization. So you've got energy out. Now, the second law of thermodynamics has often been stated as there's no such thing as a free lunch. Here, we get not only the free lunch, or free usable energy, but get paid for it. Getting rid of thermal pollution makes your heat engines more efficient, so you're getting double benefit. The only way to save the second law is to ascribe an entropy to the black hole. As we feed the black hole our useless thermal energy, say E, we increase its mass by delta M equal to E over C squared. So the reduction of entropy of the universe is by delta S equal to delta M over T, where T is the temperature of the black hole. This must be the increase of entropy of the black hole. Now here Penrose ran into a problem. What is meant by the temperature of the black hole? He conjectured that the entropy would be measured by the Weyl curvature tensor, which gives the pure gravitational field without any contamination by matter. However, the Weyl tensor is trace-free, so you can't construct a scalar from it directly. You would have to go to the quadratic expression, not take the trace, but take the inner product of the Weyl tensor with itself, and that would give you a scalar. So it would be a quadratic. That created problems, and he never managed to resolve them. It would anyhow not have been, it would have been ad hoc, nothing automatically obvious about it. So now people talking about the history of black hole thermodynamics discuss whether Bekenstein or Hawking was first to introduce thermodynamics into black hole physics. However, totally ignoring that Penrose had already talked about it in 1968. Bekenstein is 1972 and Hawking 1973. In fact, what had happened was that Penrose had talked of this already in Princeton in 1968, and Wheeler was there, and possibly Bekenstein, and so between them they heard it. And Wheeler was Bekenstein's PhD supervisor. It appears that Penrose had forgotten that he had presented this idea before the others, and his biographer wasn't able to find record of it. He regarded this as unimportant. He was always very generous in giving credit and had no greed in taking it. I mentioned this to Leonard Susskind after reading his Black Hole Wars. He said it made sense and explained some things about the history of the subject that seemed odd. Now, my first paradox that I constructed. According to the standard view of black hole physics, from outside we cannot see an object enter into a black hole. This is because the light from it will be infinitely redshifted and infinitely time delayed. So it would then not be possible, supposedly, to see it. Now, this is the Hawking temperature, what Hawking had provided for the black hole temperature. And suppose that there is Hawking radiation. I want to do an argument to say that that would be counterintuitive and wrong, etc. There is a black hole mass such that it would radiate at just above the cosmic microwave background, which is 2.725. And so let us say this is at 3 is the mass of the black hole. Now we throw a stone. I don't suppose you've ever seen a stone like that. That's the one I've made. There's a stone and it's falling into a black hole. It looks like a cloud. Okay, so that is thrown into the black hole, and its mass is chosen such that the Hawking temperature for the masses put together is 2.725, and so the shining black hole will switch off, because before the stone falls, it's shining at 0.275 degrees Kelvin above the background. Once the stone has fallen into the black hole, the radiation from the hole is effectively switched off, and it merges into the CMB, and we cease to see the black hole. Thus we have seen the stone fall into the black hole by the shining black hole vanishing, which we cannot do. So now what went wrong has to be looked at over there. This brings out the question of when the black hole forms and when the black singularity forms. Because when I throw the stone into the black hole, supposedly it falls all the way. I don't see it fall, but it has fallen in. So the mass has increased. We can see exactly when it falls in. In a later diagram, I'll just point that out. So the matter falls in. There will be a back reaction, however, leading to radiation of various frequencies with various time delays. So how can we tell when this radiation has stopped and Hawking radiation started? That was the first problem. The second one, an observer falling freely into a black hole will see a flat or Minkowski space-time. As such, the black hole does not seem to exist to that observer till the time that the observer hits the singularity. Of course, tidal forces would be felt if the observer is not a point, but if it's just a point, no tidal force. As such, this observer would not see any Hawking radiation, but a fixed observer would. Now, you think of a screen here falling freely towards this black hole. This is S1. And there's another screen which is fixed relative to the black hole, far away and just fixed. So this falls freely, and now this screen here is in the shadow of this screen, and now the radiation from the black hole is seen by S1 but not by S2. It's not seen by S1 but is seen by S2. Despite the fact that S1 is in the shadow of S2, I think I've said this, S2 is in the shadow of S1. I've put these upside down over here. So it should be S2 where it's S1 and S1 where it's S2. How can the radiation seen by S1, well, that's S2, reach it but not pass through S1? Here, how can the radiation go from here to here without passing through this. It's not seen by this. It's supposedly come from here, and it's seen over here. So one has to suppose that the radiation does not travel from the black hole to the S2, as it was shown there, but it gets there non-locally, automatically from one to the other without going from one to the other. It's all there. Somehow you have to put that in. If it comes non-locally, when does it appear? It hasn't traveled, then when does it appear? If it is produced by the gravity of the black hole, how valid is the assumption or approximation that we can ignore quantum gravity and accept the result as correct? Only because it gives meaning to the entropy of black holes required to save the second law of thermodynamics from the clutches of Penrose's black hole civilization. Should that be good enough for accepting? So these are the two paradoxes. Now the Carter-Penrose diagram I'd like to introduce by just saying, when I went to ICTP in 1975, I was asked to explain Penrose diagrams as a student of Roger Penrose, so I should be able to. I was writing a paper entitled Penrose Graphs, a name that I had given for the space-time representation of twistor scattering diagrams. I thought I was being asked about the energy momentum representation diagrams that McCallum and Penrose had written a physics report about. That was my assumption. However, that wasn't correct. It turned out that this was a name given to the conformally compactified space-time diagrams that Penrose used and which had been extensively studied by his student Martin Walker, with my help at a little bit, which I am very pleased to have put in there. The name had been given by Hawking and Ellis in the large-scale structure of space-time. Now, Penrose never claimed to have invented the diagrams. He told Hawking that the diagrams had actually been developed by Brandon Carter. So after that, Hawking called them Carter-Penrose diagrams. And Walker was still forgotten, being just a student. Well, that happens to students. And much worse has happened to students. The usual space-time diagram for the Schwarzschild black hole is shown in this adjoining diagram. The vertical axis here is the time axis, and this horizontal axis is space with one dimension suppressed. So matter falls in this way over here, and then as you go here, it would fall in. So this will become denser and denser and denser till it comes past here. Once it has entered the Schwarzschild radius, no light even can go out, and so from outside you see the black hole formed at this stage. If afterwards you throw something in here, it will go on a path like that, less than 45 degrees, and it will fall in that way. And it will go practically right angles right here. So that's the way it would fall in, and that's what I was talking about, that if matter fell in, then the mass has increased. You may not see it fall in, because if this was falling this way, the light from it would not reach you. It would appear to be stuck right along here, and you would never get to see the thing falling in. However, supposedly, somehow or the other, it has fallen all the way in, and now the mass has increased, and that was how I said there's a problem with the argument that uh, one can have the not see the thing falling in. It would be seen. The short shield radius here is normally denoted by RS. This diagram won Roger Penrose the Nobel Prize. The problem with this diagram is that the coordinates break down at r equal to rs. This is seen as the Schwarzschild metric becomes singular there, because when you put r equal to rs, then this will become 0, this will become infinite, so the coordinates are singular. There's also a singularity at r equal to 0 here. Now that other singularity is separate, but this singularity is just due to a bad choice of coordinates, like the singularity of a plane at r equal to 0 in polar coordinates, and you can get rid of it by going into Cartesian coordinates, for example. Martin Kruskal developed null coordinates that went through the horizon like a hot knife through butter, using null coordinates like the usual retarded and advanced times for the electromagnetic four-vector potential. These. For the Schwarzschild metric, you define dr star in terms of dr this way. And then you use r star in place of r. All you'd have to do is now integrate, and so when you integrate this, you'd get r star. When you integrate this, you'd get the function of r, and that you put in here. This change was introduced independently by Eddington and Finkelstein. Oddly enough, 25 years later by Finkelstein. You might wonder how come. Using only u or v gives non-orthogonal coordinates, and using both still leaves the singularity intact. Kruskal exponentiated these coordinates, vu capital and v capital in terms of the small u and v, and then got this, which is non-singular. And this is depicted over here. Well, since minus infinity is less than u and v less than infinity, this diagram is not easy to see. It sort of spreads out all over the place, and that side and that side, so you can't really get a hold of it. Brandon Carter wanted to see it easily as a whole, and so he took a compactification, and with that he got what are called the Carter-Penrose diagrams. And for the Schwarzschild metric, this is the Carter-Penrose diagram. I've essentially explained through the mathematics there how it went. What it amounts to is there's this horizon, this parallel or anti-parallel, forget about. This is that if you're going from here in, you have something falling into the black hole, which I was talking about, that stone that looked like a cloud falling in. It would go like that in this diagram. Here, this is past infinity, time like past infinity, all the way back. This is future time like infinity. I've got it compactified so I can talk about infinity itself. I0 is space like infinity, all the way space at 0 time supposedly, but if there was any other time, you'd get something that went like that, and so this would remain the same. In any other frame it would look different, but it would always be here. This would be the black hole, and this is the time reverse black hole, so what would be called a white hole. Nothing can come out of the white hole, but there would be this complete picture to be made. This is Scry minus is null infinity. u equal to 0 or where u equal to 0, v equal to 0 here, and then these are where it's gone u equal to v, r equal to t equal to infinity. So it will be null, but it would be r and t going infinite. Here it would be minus t, infinite negative time, infinite positive time, n equal to r. There's scry minus, that's scry plus. Notice I haven't got any such thing over here. What are these? I don't know. That was the problem of the ambiguity. The Carter-Penrose-Walker diagram, as I would like to call it, is this I minus here, I plus given this way, I0 given this. This is R equal to minus Ct equal to infinity, R equal to Ct equal to infinity. So this is all very well. This is the usual universe outside the extreme right. But look at this. How about over here? This one, what is this? For that matter, what really is this? This was not so clear. This region had been required by Einstein and Rosen, noting that all GD6, the shortest paths, must either go to infinity or end at a singularity. This was not satisfied without this region. So you needed this part only for completeness in some sense. We'll just see in what sense. You see, this is what you'd have with the outside universe looking like that, and then if there's the black hole, it just gets all pulled in, and then there's nothing over here. There's the Schwarzschild radius, and suddenly there's just nothing. Now you can't have that nothing, these GeoD6 suddenly finish. They can't end, so you have to then have something that will allow them to get together, and so you need to complete it by putting the opposite, turn it round and put this with this. Now you'd get that diagram. And this would be the final thing which had been taken by Einstein and Rosen, and this is called the Einstein-Rosen gauge. So the upper part corresponds to the spatial section of the usual universe, and the lower part to the maximal extension. And this is the fourth region in the diagram. This one. Incidentally, that's the white hole part as I talked of down here. So there's the ambiguity now in labeling the Carter-Penrose-Walker diagram. Let us go back to this and my claim about the ambiguity. If the question of the significance of the fourth region was $1 million question, this $64 million question is, what do the left vertices represent? The right vertices were fine, what about the left? In 1988, I found no unique answer to the question. It depended on how I viewed the space-time as to whether you label them one way or another. MTW did not help. Hawking and Ellis with the large-scale structure didn't help. So I asked Penrose and I asked Wheeler. There are two ways of looking at a space-time. From the point of view of the observer, which is a local way, and from the point of view of the space-time as a whole, which is a global way. In both cases, we have the whole space-time by the end of it. So there's no a priori to decide which to use. For A, we need to define our preferred class of observers and then take the collection of all of them to give the space-time. I consider a class of observers falling freely from infinity starting at rest. So they start way out and they just fall in freely. This corresponds to breaking the space-time into a sequence of space-like hypersurfaces of zero intrinsic curvature. The three-dimensional Riemann tensor is zero. For the second, I took the breakup by hypersurfaces of constant mean extrinsic curvature, which is this. Okay, there's the extrinsic curvature tensor, and so you want the mean extrinsic curvature. That's the trace. That's the divergence of the normal vector, unit normal, and so that is how you define those. Now, in the former way, which I talked about, you would have this picture. This is that same I minus, I0, I plus, sky minus, sky plus, the horizon here and here. So this is all you'd have, and now if you want to get the other part, all you have to do is rotate this round, turn it upside down, and get this. Now join these two together, and that would be the Carter-Penrose diagram. Clearly here, this would be the same time. So if this was I minus, this is I minus. This was I plus. So this is I minus, past time like infinity, future time like infinity. So time is going this way at r equal to 0 in this diagram. Here it will be in reverse. Time is going this way. This is the direction it will go in, and this is I minus, this is I plus, and so you'd have the time going that side. It will go the other way around. And anywhere in between, it will have to then go the other way around. From the maximal extension, this is how it will go. So here is the picture that you would get. And this is where you can really see it, that you have these hypersurfaces of constant mean extrinsic curvature, which give you the same time that Rijk equal to 0, and these are the ones that will give you the same time everywhere. So this would be the same time. This here, as it goes, this would be the same time, and this would be the same time. Rotating this 280 degrees, as I just showed, this gives you the full diagram, and these two parts don't talk to each other. This part and this part, they just separate. And so this is one way of looking at it, so only half is there. This was pointed out later, considerably later, in a talk by the Nobel laureate Gerard de Hooft, and then I think people thereafter started taking notice of this work. Now consider the other way, the global way, where I don't say I'm going to look at the thing with constant, with zero curvature, intrinsic curvature. I'll take constant mean extrinsic curvature. This was defined by Jim York, and it gives you then the York time as you go forward. This breakup was obtained by my students Amjad Pervez and Azad Siddiqui. Unfortunately, Amjad is now deceased, and this one, they and I did this work, and clearly here the left corner is I minus and the upper I plus again, because here the hypersurfaces will go this way So if this is I plus, this will be I plus. This is I minus, this will be I minus. So it will go the other way. These are the mean extrinsic curvature hypersurfaces that we obtain. And this is typically the sort of thing that you'd have. So it would go I0 to I0 and I minus here to I minus, I plus to I plus. And that's opposite to what we were getting the other way. So for obtaining equal time commutation relations for quantum field theory, what equal time is to be taken? This is obviously vital because you can't just say equal time without specifying what you mean by equal time. So if you mean by equal time the local interpretation as the observer sees it, half the diagram is lost. Now this creates spurious fields where the horizon comes. There'll be spurious fields, and this was noted by Fulling using the Rindler wedge in this paper. In B, the full maximally extended spacetime does not get spurious additional fields. That's a different way of looking at it. Hawking took the former view, the earlier one. So then you've got a horizon, and the horizon is giving you the fields. Now, incidentally, people claim that supermembrane theory gives the entropy of black holes according to Hawking's formula, and hence supports Hawking radiation. However, supermembranes yield two-dimensional metrics that only have a form similar to the Schwarzschild metric, not proving that they actually represent black holes. You'd need to check that. Of relevance is this cut and paste model of a black hole in a closed universe. Here's the closed universe, and you cut out a piece of it and replace it by this very dense region, which will become the black hole later. And so you then have junction conditions to join here, and you can watch the evolution as it goes. Then this will, at some stage, become a black hole. So this is the denser region, this is the Schwarzschild region, and this is the less dense region. We can follow the evolution from beginning to end. That's done by John Wheeler and I. The corresponding CPW diagram is given in three parts here. This is the dense part, and this is the rare part, and in between there'll be the Schwarzschild part here and here. Now, this region C, you'll see in Schwarzschild coordinates properly, but then in these coordinates, the Carter-Penrose coordinates, you'll see this region opening up, the Schwarzschild region opening up as you go. Here it is all stuck at one place, there it's gone off to infinite distance. Two complications are faced in foliation. One is the sensitivity as you numerical instabilities, and the other is the larger number of steps of computation. So you've got two problems, both have to be dealt with. The problem is not merely the numerics. The proper length along the hypersurface of the Schwarzschild part increases as the singularity is approached. For the Qadir-Wheeler suture model, a Schwarzschild region sandwiched between the two Friedman models, it was shown, Athiyatullah Hussain and I, that delta S rose as k to the 1/3. So as you go with k going to infinity, delta S goes to infinity. And the pure Schwarzschild black hole, it was shown that delta S rose as k to the 1/3 log natural k. Why the difference is log natural k? Well, you see, in the pure Schwarzschild case, you go right to the ends. In the suture model, you cut out the ends and you only take the part inside. So the part inside is what will go with this, and the total for the Schwarzschild region will go this way. So both go infinite, so you'd say, what's the big difference? How about the volume? A detailed analysis shows the radial parameter of the black hole shrinks with k, giving the volume as k inverse log natural k, and so the volume goes to 0. It in fact collapses. Even though the length is going infinite, the volume is going to 0. So we do indeed get a collapse with time for the suture model, despite the proper length diverging. So far, no problem still has emerged. Now extend to an n-dimensional space-time. In that case, one obtains the volume going k to the 1 minus 2n over 3 log natural k as the hypervolume of a hypersphere in n plus 1 dimensions. So for n equal to 2, you get v going only logarithmically to 0. So still it goes to 0. But now go to n equal to 1. So that's the n plus 1, 1 plus 1 space-time. And here the volume goes k to the 1/3 log natural k. You can't tell me that's a collapse. The 2D black hole doesn't collapse, it explodes. I can't help it, that's the way it's going. Very clearly, it explodes. No collapse, but an explosion. So is there Hawking radiation? Penrose had no formula for his black hole entropy. Bekenstein obtained a formula that gave entropy as proportional to the black hole area. Hawking obtained a temperature and the constant of proportionality for the entropy. If Hawking's result is spurious, why does it give the entropy? That would be the argument, saying it's really not valid, then how does it give the entropy? I'm suggesting that the total result may be that the contributions of all other fields and quantum gravity exactly cancel out. In that case, essentially performing half the calculation may provide us with the entropy in a manner similar to that of getting string tension using D'Alembert's principle, so that you just have it static and then you get it there. Notice that in flat foliation, we got time reversed universes, and so the energy would also get reversed. And Hawking only looked at the positive energy part, but the missing part would have negative energy. Physically, why should it cancel instead of adding? Maxwell noted that the electromagnetic force, and hence its energy, behave opposite to gravity. At that time, gravity was the better known thing. So electromagnetic charges repel, but gravitational charges always attract. Gravitational binding energy is negative. We know that. Therefore, it should be that there would be the Hawking radiation balanced by the quantum gravity side. Hawking explained his radiation as quantum tunneling of particles from inside the trapped surface to the outside, like prisoners tunneling out of a prison. Not by paying bribes as we do here. There's the tunnel out. So I point out that quantum gravity may provide a force of superheroes who go after the prisoners and bring them back to prison. Radiation without radiation is in my paper 2019. Einstein had argued with Bohr about the interpretation of quantum mechanics and claimed that it is incomplete. Hawking used his radiation to revive the argument for incompleteness of quantum mechanics. The argument is that one can throw a pure quantum state into a black hole, and the black hole will radiate it out as a mixed state, violating unitarity. Since quantum evolution requires unitarity, quantum mechanics is not internally consistent and hence incomplete. Foliation shows that it is the space-time, not quantum mechanics, that is incomplete. Now, Hawking had bet Neil Turok that his argument would prove correct. That was the bet that he admitted to later admitted to losing. In this, Susskind proposed his black hole complementarity principle to explain why information would appear lost to the outside observer, but information would not actually be lost. It would appear lost to the outside observer, but overall the information is there. If the space-time is anti-de Sitter, then it would be holographically kept at infinity around the horizon. So that would be stored there. That's the holographic principle. So my conclusion here, by Penrose's argument, black holes must have entropy. Bekenstein provided a formula for the black hole entropy up to a constant. Hawking argued that the black hole should radiate at a temperature corresponding to the entropy and giving the constant. I've explained why there is doubt about it. It is claimed that wrapping the 2D black hole in a supermembrane also gives the entropy. However, we've seen the 2D black holes are not black holes at all, because instead of collapsing, they explode. So if we are left without the brains to get the entropy, we do not have a Hawking temperature to give meaning to the entropy. Can we talk of the entropy and provide a formula for it? And I say yes. If we have no dynamics, the same arguments would say, can we talk of string tension? Yes, we can, using D'Alembert's principle. Similarly, it could be that the quantum gravity effects would exactly balance the effect of quantizing other fields in the curved background. But if we have no Hawking radiation, would it be impossible for anything to come out of the black hole and the black hole to disappear? The idea behind constructing the Qadir-Wheeler-Sucher model was to verify Penrose's conjecture that the black hole and big crunch singularities are simultaneous. Open universes were incorporated by Penrose's argument by taking a conformal transformation where you get it compactified. In that case, the black hole singularity would never form in some sense. It forms at infinite time. Conformal time it will form. What happens to the Hawking radiation on foliating the open or closed models? Wheeler was not ready to consider it because he believed the universe had to be closed, because only so could intelligences in the universe create it by observing its beginning as he thought was required for the quantum theory observer participation. So that was his view. There's the basis of Wheeler's philosophy. There's the Big Bang, there's the Big Crunch, and you go along this universe, and you, from here, all the intelligences near the end of the universe see the Big Bang, observe it. By observing it, they create it. if you don't want to believe that, I don't blame you. But that was Wheeler's way of seeing it. I left it alone, but Susskind encouraged me to revive my nearly classical resolution that I had let be because of Wheeler's uh, religious preference there. But it would be worth looking at. And so, thank you. I have gone over time, as I said I would, because of the shortage of time at the beginning. I couldn't help it. So, fine, thank you. And Naresh, you said there'd be questions and answers.
Yes.
Now, as you know, you'll hear the questions.